Looks like we're just about there. Welcome back, everyone. It's official. Looks like we can start. Welcome back, folks. So today's class, we're starting off. Oh, what did I do here? Sorry, I need to redo this box. Where we're really at is right here. We're going to start looking into chapter 14, dealing with just more confidence intervals. This time there'll be confidence intervals when we're dealing with quantitative data, so the one for the population mean. After we get through this, it'll probably be after we complete our third exam, we'll start working on hypothesis testing. Well, any questions at the moment, folks, with where we're at? Okay, I guess for the other side of the announcements, we have quiz number 8. This one was pushed back to a later due date, is going to be officially due next Thursday, or this coming Thursday. We'll be posting a new quiz down right over here, and that one will be due on the Thursday of the exam week. But if folks want to solve that quiz a little bit faster, I'll make every effort to get a grade and return back to you, because that quiz is going to be based off of chapter 13, the very last problem pretty much on doing a confidence interval, which means it's basically a guarantee that a different problem, just like that one, is going to be on the third exam as well. So if you take care of that quiz right away, as soon as you're able, I'll grade it as fast as possible. So that way you'll have really great feedback on that kind of problem going into the third exam. And like we mentioned before, for the third exam, we're going to do another informal review day on the 7th, Thursday. So come armed with questions and we'll spend as much time as is necessary answering them all. Other things that I've been doing on this Moodle website is this document right here. This came in from a comment that another student mentioned that getting the ISU book bundle reinstated is not actually possible, I don't think. And the book costs about, I think, $125 at least. So people are having a hard time getting a hold of that. I mean, the steps to do it, even if you have the money, are not straightforward or easy. This is another option. It's not the best option, but it says here, the files in this document are intended for students who opted out of the book bundle and you currently don't have access to my lab. So if you haven't been able to do homework problems for that reason, click on this right here. And it's just a bunch of either a Word document or a PDF document, pick your favorite type of document, having the same exact problems from my lab. So if we open up, say, this one right here, this is what it looks like. This is the same exact problems in my lab, but now it's basically just a printout. So the way you could solve this is you could print just this out, mark your questions, and then hand it in. Or you could just take ordinary lined notebook paper and say, on the top, chapter 14, problem number 1, part A, and just mark your response. That'd be totally fine as well. Then you can hand them in just like you hand in your quiz. Either drop a hard copy on the desk here or send it to me by email. Another thing that will happen if you decide to go this route is, well, there's a huge fairness issue at the same time, right? In my lab, you have multiple attempts, unlimited attempts. On these, the way to kind of make it more fair, even if you miss a question on these, I'll hand it back and you're allowed to just redo that assignment as many times as necessary. That way, there's not a fairness issue with people being able to have unlimited attempts in my lab, but not on that. So that's how these documents go. If something looks a little bit off here, keep in mind, these are all screenshots. So I could have missed something or something extraneous could have entered in the screenshot that didn't have to be in there. But they go from a section by section basis all the way up to chapter 14, and I'll post new ones as we go further in the class. It went backwards as far as chapter 6. This is about when I had estimated people lost access. So if you're missing, say, section 5.4 earlier, anywhere else in my lab, just let me know and I'll publish more of these. Well, any questions, folks, about working with those documents there? Doesn't apply to everyone in the class, but. Okay, so let me go back over here. I think we are right about here. Okay, I think that's all of my announcements finally. Any last questions or comments at all, folks, before we get started? Okay, let's jump in then. So we are in, where are we? Chapter 14, we're moving through the course. And chapter 14, same kind of stuff as usual. I mean, these documents seem awful every time you open up a new section or chapter in a statistics class, but it's always just about getting us up to speed on all the prior information. And as far as that goes, let's mention what we did in the past and what we're about to do, just to get some parallelism going. In chapter 13, we have a confidence interval that goes like this: p hat plus or minus z star times a standard error of p hat. And this is an estimate for p. In chapter 14, here's what we're doing this time. Chapter 14, we're taking the statistic y bar, and our goal is to estimate mu. So in our confidence interval procedure over here, we first put down the estimate. Our best estimate of y bar, or excuse me, of mu, this one right here, is y bar. So the sample mean is something we calculate and we estimate the unknown parameter with, mu. But now we have to add and subtract the margin of error. And this is going to look similar. We need a critical number. Slight difference though. The critical number doesn't come from the normal distribution. It comes from a related distribution called the t distribution. So we put in t, call it t star. And the other change is we don't have the same standard error. We're putting in the standard error of y bar. So before we can really get into the confidence intervals on these notes, we have to discuss what in the world is t star? And we have to discuss what is the new standard error. And really to get to any of that, you have to start here. The central limit theorem, this time it's for means, but a very, very similar statement. These are super abstract theorems. They're the only ones that I put in a box in this class. So before we look at that, here's another way to think about the central limit theorem. In chapter 13, we use a giant calculator to just generate histograms. But for this one, I felt like it'd be better just to go with a simpler screenshot. This came from a different book, so here's the source down below if you're interested. Probably a great textbook for a second course in statistics if you just can't get enough of this stuff. And here's how this goes. It says in the definition, assume you have a simple random sample. The sample size is n. That sample size n is duplicated here all the way down on every one of those samples. So we keep that sample size fixed. It comes from a population we're interested in. There it is. That's the population. Could be students, fish, who knows. The sampling distribution of a statistic then, they're referring to this right here when they say sampling distribution, is a brand new probability model or probability distribution. It contains every possible value that the sample mean could take. By the sample mean, we mean y bar. So our sampling distribution aggregates all possibilities of what your sample mean could ever be, even before you go to collect your data. So here's the type of experiment that we actually used technology before, but now it's just a picture. We have a certain population, and we go to take a sample of size n. So this represents one experiment occurring. You calculate your statistics, y bar and s, but we take just y bar and visualize it going into the histogram like this. There's sampling variability. So if you go to a different study, same sample size every single time, calculate y bar again, this is saying, well, it doesn't have to be the same exact value. It could move to a different location. But if you keep on doing this over and over again, that's the dots here. Imagine doing it, say, 10 million times or something like that. You start to get a shape that goes about like this. It doesn't look much like a histogram as you do this more and more. The rectangles in the histogram get narrower. They look like saw teeth, and eventually an actual curve emerges. That's what we mean by the sampling distribution. So let's see if we can make that curve look a little bit better. It'll eventually look something like this. It'll be totally symmetric, unimodal, so one main peak, and the center of this turns out to be mu. Somewhere in the middle. Mu is unknown in these problems, but so that's what makes it interesting when you calculate these y bars. It's almost like a shotgun. You take a whole bunch of samples And all these values settle around mu, like shotgun pattern essentially, but they are typically closer to mu than anything. Other thing that's kind of suggestive about the curve being drawn is it looks like this is the normal model. So we can say it's normal. Mean is mu. But here's our big struggle so far. This takes a lot of work to find, and that's what the central limit theorem is all about. The standard deviation is anyone's wildest guess at this point. So if we can come up with that standard deviation, say what it is, then we'll turn it into a standard error, and that's one key to the entire confidence interval in chapter 14. We already know how to do Y bar from chapter 2, for example. So that's what the setup looks like. And with this picture right here, the normal model, finally down here on the central limit theorem, this is what's being said. When the sample size is large enough, then the sampling distribution of Y bar, that histogram we saw, is well approximated by an actual normal curve or normal model. Even if the underlying distribution is not normal, that's still true, which is a very incredible fact. In fact, your underlying distribution could be skewed, severely skewed. Let's take a look at one of them. This is a sample, but we can imagine the population would look about the same. And we have something super skewed, I think. Let's see, probably in shape. There it is. So this is a heavily skewed sample. But let's imagine this is what the population looks like as well. Highly right skewed. If we sample from this population, most people would say the sampling distribution here wouldn't be symmetric. It should be skewed, right? It turns out that's true, but as the sample size gets larger and larger, it turns out the shape of that sampling distribution does turn into a normal model. It does become symmetric, even when you're coming from a worse population like this. It doesn't matter how skewed it is. The larger your sample size gets, the closer we get to the normal model and being able to use the tricks that we would like to come up with a confidence interval. So this makes it kind of tricky because now we wonder, when is n large enough? And this is just a really rough rule of thumb down below right here. For most situations in the sciences, central limit theorem is effective at a sample size of 30 or larger. Doesn't mean that's a requirement. That means if we don't know how skewed our population is, that's a good rule of thumb to go by. Well, any questions so far, folks, with the rundown of this new central limit theorem? Okay. Other interesting things we should talk about are this part. Rule 1 says the mean of Y bar, let me see if I can zoom in on that a little bit better. There we go. The mean of Y bar. What this is saying right here is the sampling distribution of Y bar has a center, which is the unknown parameter mu itself. That's what we express right here when we put mu in the center. So that's all rule 1 is about. Rule 2 is a little bit more exciting in my opinion, because rule 2 has the major thing that we're looking for. Sorry, I'm trying to get just the right color here. Let me remind myself, we use green for standard deviation. So it tells us the standard deviation of that normal model is sigma, the standard deviation of the population, divided by square root n, where n is the sample size. And I'm noticing here on my notes, I got Y bar corrected here, but this one missed me. It should have said the sampling distribution of not X bar, but Y bar. One day I'm going to get all of those, and then they'll switch the book on me. But anyways, sorry about that distraction. So that's our central limit theorem. We have one of our major things that we wanted right here, a standard deviation. Well, now that we have that, here's the next major problem. The central limit theorem is going to allow us to potentially write down a confidence interval that would look like this. In fact, back in the past, confidence intervals did take this shape. It wasn't a problem, especially if sample sizes are around 30, even around 20 or higher. No one noticed that this is actually a pretty flawed confidence interval. But right away, you might have noticed that there is a major problem that people probably didn't bring up a lot in the past. Anyone see what the major problem is of that confidence interval? it's not Z star. We would actually use the same Z star table in chapter 13 if we could use that confidence interval. So something else about this is a little bit off or just fishy. The square root right here, not too much from there, but you're in the right direction. Square root came from up here. But the trouble is, well, let's think about in these terms. Would you say y bar is a statistic or a parameter? It's kind of tricky to think about, right? That's what the purpose of these notes are up here. Let's take some of these down and think about that problem as we go along with it. So let's go right up to here. That should do the job. So now looking at, yeah, that y bar here is a true statistic. So the trouble is in that location, Z star, we know how to grab those. Right, sigma is itself a parameter. Now we're starting to look at some trouble. Imagine, how would you calculate this? We can get the sample mean. We just crunch it from the data. We can get Z star from the table in chapter 13. We would know the sample size, but sigma is a parameter and it's unknown in this problem. There's where we have difficulties, right there. Since sigma is a parameter, it is unknown. And this is similar to when we say mu is also unknown. You want to use a slightly different color pen. Mu is also unknown. If we knew the values of the parameters, we'd have no reason to do statistics at all. So we would just be done with the semester. So that's the trouble. And what did people do in the past? They estimated sigma. Anyone see what the best estimate of sigma might be through all this stuff here? It wouldn't be mu, but you're on the right track. We have to grab one of those things. What we can say, though, is that mu is approximately y bar. So we want to do the same kind of thing and say, well, then what's sigma approximately equal to? Exactly. So this S is the standard deviation of the sample. Sigma is the standard deviation of just the entire population outright. So if sigma is unknown, we go to the sample and estimate it this way. Sigma is approximately equal to S. And that's literally what they did historically. They went right here and they dropped an S into that location. So we start to wonder, why can't we do that? What's wrong with doing that? It turns out that is actually a really massive problem, and it only gets noticed with small and smaller sample sizes. If you put just S there, what goes wrong is the critical number is not Z star any longer. We no longer even have the normal distribution. That's kind of a sad fact, in fact. So let's say here, since sigma's a parameter is unknown, what we really should be doing is this. We need to derive a formula for the standard error of y bar. What it approximates is the standard deviation of y bar from right up here. So we can say next, standard error of y bar is equal to, now we're following the steps that people took in the past and put S over the square root of n. So that's our brand new standard error. Again, this was trouble though. As soon as they put in S here, Z star was no longer correct. And it turns out the first person who discovered this fact, let's go to the Moodle website just for a moment, is this person, William Seelig Gossett. He worked for the Guinness Brewing Company, and he was working with really small sample sizes. Small sample sizes in the order of sample size 4, sample size 5, even sample size 3. And when sample sizes are that small, it became very apparent that this confidence interval is wrong. Even if we use the standard error, it's not giving the right answers. And they could tell because they would run an experiment with alcohol and yeast and all that stuff. And months later, they would see that the results of the experiment didn't match up with their expectations. Not at all. Something was wrong. So this is what William Gossett did. He invented a new distribution called the T distribution, but he worked for the Guinness Brewing Company, and that company said, you cannot publish this. They didn't want other brewing companies to know about this knowledge. So William Seeley Gossett publishes it anyway under the pseudonym Students T Distribution. So now he's committing corporate espionage. I mean, for real, corporate espionage in 1924. He communicates with Ronald Fisher, a major statistician, and this method that we're about to discover starts to actually take hold. So that's what's going on with this T distribution whenever we talk about this right here. This is a distribution discovered by William Seeley Gossett. Let's say it this way. Discovered by Gossett, and he violated his company's contract to publish. But we're all kind of glad he did. So that's why I said on the Moodle website, he's a pretty dang good role model for people in the sciences, because sometimes if you know you're hanging on to information that's so important, so earth-shattering that this interval is totally wrong, the world deserves to know, even if your company you're working for doesn't agree with you. That was what Gossett decided at the time, and people tend to agree with them. So now we're going to take a look at the T distribution, discover some of its properties, and we'll see how to calculate a critical number T star based on it. Any questions at the moment, folks, before we take a look at the T distribution? Okay, so it says here, the T distribution corresponding to any degree of freedom, we'll say more about degrees of freedom, is bell-shaped. That's good, so is the normal distribution. Centered at 0, so is the standard normal distribution we get Z star from. So that's all good. Let's take a look at it right here. The document is normal and T distributions, only for the sake of demonstration in class. It's really a PowerPoint converted to a PDF, so it looks kind of funny. So here, when we refer to the T distribution, we sometimes write it this way, T and then the degrees of freedom is here, n-1. We'll compare it to the normal distribution with mean 0, standard deviation 1. So the first slide looks like this. I guess there's a better way to run this. I think left arrow, right arrow makes this better. So looking at what we have, it says the graph below, yellow is the normal model. So this is the normal distribution, and blue is the density curve for the student T distribution, the one that Gossett discovered. This is at sample size 2, and that's a very, very low sample size. That's practically anecdotal data. But at sample size 2, you can make already a couple interesting observations. Once I pick a pen, let's go with, pink will do the job. So now let's imagine on this graph right here, the red dot is the normal model. And let's say you're doing a confidence interval, say C equals 0.95, so 95% confidence. If you're working on the normal curve, you'd probably be right around here and right around here to capture central area, 0.95, and we would call this number slightly less than 2, Z star. In fact, we found it's 1.96 for a little bit more accuracy. But that's relative to the normal curve. And if you're working with a different curve, the student T's curve in blue, this is what the picture turns into. We want to capture the same central probability, 95%. But notice the problem with this blue curve. We say it's heavy-tailed in the sense that it doesn't approach the x-axis as fast as the normal distribution. So to get the central 95% of area for our critical number, we're going about out here, add about out here to get the same 95% now. That means this is your T star. It's going to be way bigger. And this was the problem that needed correcting. T star should be bigger than Z star. It's going to make your confidence intervals wider. That's not a good thing, but it makes your intervals more honest now. And the predictions you make upon them are going to come true more often than not. The major reason T star is bigger here is because of, let me clear that for just a moment. It's because of this. If you just put S right here, you have made an estimate on top of an estimate. And so we should be punished. There's less certainty in the problem now, the moment we put in a whole new statistic right over here. This sort of stuff never even happened back in chapter 13, because in chapter 13, the situation's different. There is one parameter, P, and that one parameter, P, controls both the mean and the standard deviation all at the same exact time. So because of that, there's no T distribution here. But on this one, there certainly is. We're making estimates on top of estimates on top of estimates, like we said. So this is our punishment for having a small sample size and having to make an extra estimate. T star moves very far off to the right. But let's put down this picture here for the notes, just so we have something to look at if you come back to the notes. So every T distribution has greater variability than the standard normal distribution. The greater variability we're referring to is the fact that T distribution is heavier tailed. For the sake of the notes, this is N01. And this curve is T N-1. So there's always more variability in the T distribution curve, but that's good. So our intervals should be wider to make them more honest in our estimate. But here's the next key fact. As the number of degrees of freedom increases, the variability corresponding to the T distribution decreases. So here's those next pictures. So this is a sample size 2. The degrees of freedom here was 1. We go right. This is sample size 3. It's hard to see the difference, but focus on how high this blue curve is. Sample size 2, it's pretty low. Increase the sample size, and it moves up a little bit. Increase the sample size more to sample size 6, and they're starting to actually look kind of close. So if you're working with samples at sample size 6 and above, you might not notice as easily that the confidence interval was flawed. But Gossett did because he was over here, sample size around 3 or 5. There's a big difference between the normal curve and the T curve. But at sample size 6, those differences kind of go away. Right? At sample size 15, we're getting to the limit of the pixel width here on how this was printed to even tell the difference. So that's the good news about the T curve. It approximates the normal distribution better and better and better as our sample size gets larger. So it starts to look a bit like this. So it says here, as the numbers of degrees of freedom, the variability of the corresponding T distribution decreases. This is what it looks like for that variability to actually decrease. And it's kind of hard to point at these, but I'll try my best. Top curve is N01. And the bottom curve, the one in blue, I think I can point to it if it's down here, is T N-1, which is T14 in this problem. Already we can deduce a formula. We say dF for degrees of freedom, and it's defined to be sample size N-1. World's best formula. You just take one away and you've got the right answer for degrees of freedom. So that's kind of nice in a way. But keep in mind, even though the curves are still close, we still use the T distribution because T star is a little bit larger, and it needs to be to reflect the fact we're estimating sigma with a totally new statistic, S. The last comment here says, as the number of degrees of freedom increases, the corresponding T distributions approach the standard normal distribution. What we mean by that is you can make these curves as close to the same as you'd like just by making n larger and larger and larger. So as n just gets bigger towards infinity, those two curves become identical. So the last slides kind of convey that, but I stopped, I think, at sample size 30. Beyond that, you really can't tell too much. Just those two start to overlap right over here and over here. Right around here, it's hard to tell any difference at all. And notice that's the rule of thumb in the central limit theorem, which said right around sample size 30, central limit theorem is highly effective. T star is still bigger in this diagram. But here's our last slide. Make that a little bit smaller so it doesn't get too big. So now that we have the T distribution, it kind of answers a couple questions. If you have a calculator out, we can find where it is right now. Let's hit power on, hit second, and bars. And the thing we need is right here. Option 4, inverse T. The thing that's tricky about this, I think some people in Zoom may not actually have a TI-84, is that not everyone's calculator actually has inverse T. It's kind of a sad fact. The TI-83, which is a great calculator, it's allowed in this class. TI-83 doesn't have inverse T. That's really terrible. They didn't program it in. So that means we have to be a little bit creative when it comes to the homework. That's the purpose of this document, inverse T calculator. This could be used for anybody, but it's not needed if you have a TI-84. It's just up to you if you want to use it. As far as examinations go, in an exam problem, if we need to come up with a critical number, I'll print it on the exam. So actually calculating with inverse T, this is more for homework and for quizzes, not for exam settings. In an exam, I'll give you your T star. And that's just so that we could allow more calculators and not be so restrictive in this class. But let's open this document, inverse T calculator. Takes you to some random website. This seems to be just the better one that gives us answers in a more straightforward way. It works better with the ad blocker, so you don't have any kind of weird ads popping up like we have here, but I'll try my best to ignore that stuff down below. Have to see about getting an ad blocker on this computer. And there's another pop-up. So with this calculator, you just put in your degrees of freedom, your level of confidence, you hit calculate, and you get an answer out. So that's kind of nice in a way. Say, for example, you're doing 95% confidence. At 95% confidence, it's saying, hang on, I'm missing some stuff. The ads are just destroying this website. This is crazy. You need the two-sided T-score is the one that you have to use on this website. I'm just afraid to click that away. Can you left arrow? No, you can't. Thanks, Google, for destroying this website. That's pretty rough. I'll see about getting an ad blocker on this computer before I bring this website up. But what you need is the two-sided T-score. Notice it's pretty big, 2.2281. For using 95% confidence in chapter 3, it would have been a 1.9600. So that's the effect of using the T distribution. So back to the notes. Here's what the full confidence interval looks like. We have everything we need. We need for the conditions a simple random sample. Just for mentioning the rule of thumb here, at sample size bigger than 30, for most statistical problems, you have high accuracy. And it says when your conditions are met, a level C% confidence interval for the population mean is this interval, the point estimate Y bar, add or subtract T star times standard error, where that's the standard error that we discussed. Excuse me, must be the weather changing. Here, T star is the critical number that we discussed. Based off, DF stands for the degrees of freedom, which is n-1. So just an important remark on this one, we can't actually make a table of values when it comes to T star, because the value for T star changes on every single sample size and every single level of confidence. Well, we could make a big table, but it'd be a two-way table and it would be pages, just not very useful. The best practice is we calculate T star from scratch on every single problem. And we'll do that right here. So we're going to imagine in example 2, part A, sample size is 10. Level of confidence is set to 90%. Let's put in 0.90. And our goal is to calculate critical number T star. It seems important. Let's go with purple for that. Let's just leave it kind of hanging here and show what the steps would look like. In fact, the exact same steps that we took in chapter 13 to calculate Z star work here as well. You just have to make sure you're using inverse norm. You get the right work out. For the sake of just showing what it looks like pictorially, let's draw this out. So here is not the normal curve. I try to make it a little bit higher off the x-axis to say, this is the T distribution. It's based off df, degrees of freedom. So our first goal is, we should calculate that. What is the degrees of freedom? Let me actually move that down. So degrees of freedom is referring to df. The formula is, again, really, really nice. It's just n minus 1. So we need to take the sample size, go n minus 1, which means it's just a 10 minus 1 for degrees of freedom 9. So over here, we'll throw in a 9. That's part of the input into the calculator, so it's good to just write that down to have it recorded. The center of these is always 0. We're just counting standard deviations. And last thing to put on the graph is central probability of 90% would look about like that. So here's our graph so far. We're looking for T star. Right over here on the left end, that's negative T star. Here on the right end is positive T star. So that's what the diagram looks like put all together. But back to this calculator, the reason we're using inverse T is because we have the probability and we're looking for the value on the x-axis. Not a bad idea to add this to the notes, but one thing that's kind of a nice thing to think about is we're only going to use inverse T in this class whatsoever. So we'll never use T CDF, for example. So use INV T. If you hit enter on option 4, it wants two things, an area and a degrees of freedom. So we already have the degrees of freedom here. I'll say that this is input 2. df. To get the area, we're just going to use a standard trick we've done before. This calculator is only going to accept an area in the far left tail. Other calculators can take the middle tail or the middle area, if that's the case. Oh, I gotcha. That's interesting. It doesn't actually upgrade this part. So it looks like pretty much everyone goes this route. Thanks for letting me know about that. I actually didn't know. So the formula will be 1 minus confidence divide by 2 is what goes there each and every time. So in our problem, that's going to be 1 minus 0.90 divide by 2. Sorry, I'm having trouble coming up with all my little arrows here. So this is input 1, area, which is that there. So back to the calculator, we just have to throw these in. So 1 minus 0.90 divided by 2, clearly that's a 0.05, but in case the confidence is weird, it's no harm in just typing that in directly. I wouldn't want to make a mistake just on that spot. So I'm going to go and just put it in verbatim. 1 minus 0.90 divide by 2. So you can just type it into your calculator as an equation, make the calculator do the heavy work. Degrees of freedom, recall we don't put the sample size 10, we go n minus 1 and put in 9 degrees of freedom. Hit enter there, and you will get a negative value because we use the left tail area, but we just report the positive amount. So down here, we're going to say, finally, we've got T star. The critical number is 1.8331. That's just one way of doing it. Again, if you don't have a TI-84, you might not have the inverse T function whatsoever. So let's try it a different way, just on this problem, using that link I provided. Any questions at all first, folks? Okay, so if you're getting a 1.8331, then you've got the right value. If you put down on paper the negative value, that's okay too, but in my stats lab, you'd have to put in the positive value. So now that we've had that, let's take a look at this inverse T calculator. I'm not as happy with this website now that I'm looking at it without an ad blocker. Let's do one really quick Google search. Okay, click that away. Inverse T calculator. No ads. That's a really tough one because Google only wants to give you sites with ads. We have an online statistics book, inverse T distribution here. This looks like it's a little bit better. I might link this one in. So what we have to put in is the degrees of freedom in our problem. Let me see if I can move this down. Forgetting where I'm at. There we go, finally. So in our problem, if we're going to use this calculator here, we take a look at the sample size and we reduce it by 1 to get the 9 degrees of freedom. Let me just decide on a better window. So right over here, put in 9 for 9 degrees of freedom. Select the level of confidence. That could be restrictive, but these are the common level of confidences that we see anyways. We're at 90%. And it says, didn't even let me hit calculate, 1.833. We lose 1 decimal place if we decide to use that calculator, but at least there's less ads. That may not be totally fair since I think if you're following along in class, you don't have access to a random link that I just Googled out of nowhere. You're probably using this file. So let's try it one more time with the not so great link that I found. With all those ads, that seems really terrible. Google must be kind of short on their revenue this month or something. So on this calculator, put in degrees of freedom 9. Go down here, go 0.90 for the confidence interval, hit calculate, and the value you need is down here, two-sided t-score. Comes out the same, 1.8331. That's a good amount of accuracy as well, so that helps out. So let me see if I can take a screenshot. So stackology.org has sold their soul to Google, but that's okay. We still have some values. You go here, hit calculate. And then you have to be sure to go to this value, two-sided t-score. Let me see if I can put that in a reasonable way. There we go. Well, either way we do it, we've got what we want. The critical number T star is 1.8331. That means if we had further data in this problem, but they gave us a sample mean and a sample standard deviation as well, we are ready to calculate a confidence interval coming up with that number. This is the hardest part of the confidence interval in chapter 14, just getting that critical number. After you do that, chapter 13 and chapter 14 start to feel extremely similar. So one other takeaway about this number, 1.8331, is if you're thinking in terms of chapter 13, you want to compare your critical numbers. Down here, or forgot the confidence, 90% confidence, the critical number was 1.645. That means our confidence interval is way narrower for that, smaller number. But here, same level of confidence, 90%, it's 1.8331. It doesn't seem much bigger, but it's multiplying the standard error. If the standard error is big already, that slight increase to 1.8 can make your interval massively wider on its own. So again, we have essentially the same confidence interval, but we're forcing them to be wider because there are 2 parameters that we're trying to handle simultaneously. The mean is being estimated by a confidence interval, and the standard deviation is being estimated by S, the sample standard deviation as well. Estimates on top of estimates means we should be punished by having a larger number for sure, or else our interval is not accurate any longer. That was the key fact that Gossett discovered, and sciences, once they came up with that fact, were able to really grow leaps and bounds with this new statistical knowledge. So let's try it again. Sample size 190, confidence level 99%. You always want to compare these because this is something brand new. It's kind of weird in a way. So right over here, T star. But just as a reminder, at 99%, Z star, it's not what we're looking for, but we're just comparing it. Forget what it was. It's like 2.58. Yeah, 2.58 for that one. Close these advertisements. So if it's a 2.58, we're expecting something bigger over here. But there's something else happening. The sample size is gigantic, 190. And when the sample size is that large, it means your curves look exactly the well, not exactly the same, but very, very close to being exact. So although our numbers should be larger than 2.58, should be pretty close as well. So let's give it a try. So instead of writing down the actual diagram like we did above, let's do it in this way. Let me know how you feel about this. I would start by saying, let's take a look at the calculator. Let's go in the order they want things. It's second, bars. Go to option 4, inverse T. They want the area first. So let's say here, INV T area equals 1 minus your level of confidence halves. In this problem, it's 1 minus 0.99 halves. So that came from the confidence level there. In our calculator, that just means we're done. We've got the area. The picture that we did above was just to convey how it goes together, what we're really trying to do, but you don't have to do that diagram each and every time. We did them a bunch in chapter 4 when we were getting used to that kind of stuff. So next, we need the degrees of freedom. The sample size is 190 in this problem, but the formula for degrees of freedom just goes n minus 1. So we've got 189 degrees of freedom. So in the calculator, this is input 1, input 2, and we use inverse T. So let's put those in. Down below, degrees of freedom go from 9 to 189. I think we're about ready to compute this all out. So it should look about like this in this calculator. And as a result, notice how it actually takes a second to compute. That's worth redoing again. Let's hit second bars, go to inverse T, and watch it as you hit enter right here, what your calculator does. It actually hangs for a minute. This is a huge computation for real, actually. It's why the TI-83 doesn't have inverse T. TI-83 can't calculate the inverse T. It needs a better chip. That's kind of an amazing statement. So this is a tough computation, but the value we report, it takes a calculator a couple seconds, is 2.6021, rounded to 4 decimal places, getting just the positive value once again. Oh, strange. There's got to be something with maybe the confidence or the area. Let me try it again as well. It could have been me. So second bars, go to inverse T. Oh, I went inverse norm on accident. Let me try again. Second bars, hit option 4. That's the faster way to get there. Clear that. We don't need anything. Oh, geez, I hit it wrong again. Let me try again. Second bars, option 4. How am I missing that? Yeah. Oh, I'm on inverse norm on the top. I see what's happening. If this happens to you and you feel like you're stuck in a loop, hit clear, hit second and quit, and then that cycle is going to end. Second bars. Just going to scroll down to it to be really sure this time. We're back to inverse T. If that happens in an exam setting, let me know. That's a situation I can help out with the calculator if it's just behaving weird. It was actually working correctly, but it wasn't doing what we wanted it to. Okay, so area, I'm going parenthesis 1 minus 0.99, close parenthesis, divide by 2.
sample size by 2 as well. I think I missed that.
Oh, I gotcha. Yeah, then for degrees of freedom, just 189, just as is. That's kind of cool though. If you cut the sample size or the degrees of freedom in half, your answer is pretty close still. So hit enter. And let me see if yeah, I still have the 2.6021 on this one. Is that what everyone else is getting so far? Awesome. So double checking, sample size is gigantic this time, but even still, when we make the estimate with the standard error, this is what happens. Our interval is marginally bigger because it's not a 2.58 for the critical number, it's 2.6021 now. So this always happens even for a very large sample size. And maybe just one more time for the folks who have a TID3 or even a different calculator, if you're using this calculator here, inverse T calculator from the website, this is what you have to put in. Sorry for the ads, we'll just suffer through it together. So degrees of freedom 9 goes up to 190. I always seem to hit that key. Confidence level is, I forgot, 99%. So for the 99%, just go here, type in 99. You have to hit calculate, and then you have to ignore the one-side t-score, scroll down through however many ads they serve you, and get your two-sided score. I'll put this in as a screenshot as well, just to convey, if you're using this website, this is what you're needing. So either way we do it, we now have the t-score, which means we can calculate confidence intervals now. Any less questions whatsoever, folks, about this whole process with those critical numbers? Okay, putting it all together, we're finally at an honest statistical problem. This is based off, I believe, the FBI website. So this is real world data, but some of the information's been obfuscated. We don't know what area this happened in. It goes on to say, the Federal Bureau of Investigation compiles data on robbery and property crimes, publishes the information in population at risk, rates, and selected crime indicators. So you could go right there if you like, if you're ever curious and you want statistical data. If you think you might go into work as a statistician, these are great people to work for. They always need data analysis. They go on to say we've got a simple random sample of 25 pickpocket offenses. So sample size deserves to be recorded. Let's write it out this way. This happens in, it says a particular area. You could say Idaho Falls if you want to make it feel kind of close to home, but we don't really know where this was at. But we do know there's a sample mean loss of $513.32. Let's go with blue on that one. So we say Y bar is 513.32. We're using Y bar only because they said sample mean. And also a sample standard deviation loss of this amount. That's going to be our S in this problem, the sample's standard deviation. So S is 262.23. So that's the information so far. And in a certain way, I feel like these kind of problems are slightly easier in chapter 13 because the context isn't as tricky. We don't have to worry about successes versus failures. We just grab the statistics they give us each and every time. The reason we did chapter 13 first is we're avoiding to do T-star until we had practice with Z-star first. That's, I think, the major reason. But in either case, we're really doing the same thing. We start with describing the unknown parameter. But we have to be careful here. It's not P any longer. That's for a population proportion. Let's say something a little bit earlier just to kind of zero in on our thoughts. If the data is categorical with two outcomes, the parameter is P, the population proportion of successes, which is one of the two outcomes. But the data is quantitative. The parameter well, it's really parameters. Let's just say both of them. The parameters are U and sigma. The one that we actually use to try to get a confidence interval on is mu itself. So that's our setup so far. So that means down below here, when we go to describe the unknown parameter using the context, we need to this time write out mu. This is the new parameter we're estimating, the mean of the entire population, which means we could start by saying the true mean, or we could say the population's mean. But because we're going to use the same value down below when we give a practical interpretation using the context, sometimes I do something totally different and just call it the true average. We know average and mean, it's synonymous. Our textbook uses mean most often than not. But if we're giving our results to the general public, oops, sorry, I didn't mean to scroll. Most people are going to understand with what you say when you say the average of something. If you say the mean of something, you're potentially going to lose a few people. They might think you're talking about something totally different. So I'll say average here most often than not, but that's not a requirement. You're welcome to use whichever stylistic choices you'd like. It'll be the true average of all. Well, we have to say something here. Anyone see what it's the true average of really? Exactly. You can kind of go backwards because this mu that we wrote down is approximated by the sample mean y bar. So going backwards to the sample mean is talking about a mean loss to pickpocket offenses. So like you said, we can say mu is the true average of all, how should we say this? All amounts lost to pickpockets. How should we say this? Pickpocketing, I guess. I'm kind of think it's a word. All amounts lost to pickpocketing in this area, wherever it was. Again, think Idle Falls or Rigby or something like that if you want the actual location to think about. So now that we have mu, it's unknown, so we can never say it's equal to 532. We have to at some point say either average or mean here because that's what it's describing. And then for the context, that was this part right here, pickpocketing due to offenses in that area. Once we have that, the rest of the problem starts to kind of just fall into place. We need a standard error. So we need to remind ourselves, what is a standard error? In this context, it's SE of Y bar. Notice all of our symbols are different, but we still call it the same type of name. It's still a type of standard error. The formula is S divided by the square root of our sample size, whatever it was. So this computation is even easier than in chapter 13. Standard error in chapter 13 was pretty tough, actually, I think. So we put in S, 262.23 in the numerator. We divide by square root of n, which is 25. That's kind of nice and almost rare. That's a perfect square, so you can just compute the square root if you want. It's just 5. So now, jumping into the calculator, we'll take in the numerator 262.23, either divide by the square root of 25 or simplify it and divide by 5. Just faster to type it in the calculator that way. And that's our standard error, 52.466. Excuse me, 52.446. So that estimates the standard deviation for the sampling distribution of our statistic y bar. This comes from another normal model entirely, and this is its approximate standard deviation. So in other words, if we pause right here and scroll for just a minute, this number 52.446 describes how spread out this is, and our statistic y bar came from this normal model, centered around the true but unknown population mean mu. Now that we have a good approximation on the standard deviation, we're pretty much done. We just need a critical number and we can write out the whole interval. So this is the hardest part. This is the reason we do chapter 14 after chapter 13, in this book at least, coming up with a critical number T star. But it's not so bad if we just follow this certain process. Input 1 is area, which equals 1 minus your level of confidence, divide by 2. Confidence level in this problem is at 95%. So I honestly think this is always a good reminder. It's kind of tricky. You have to convert your percentage to a decimal or the calculator is just going to be upset with you. So 0.95 goes there, divide by 2, and that's our input for area. Input 2 is degrees of freedom, which is sample size n minus 1. So for degrees of freedom, we go and look up our sample size up here. We're at a sample of size 25 minus 1. So that means we're at a sample of size of, or excuse me, at degrees of freedom 24. So now use inverse t, and we'll get a t star out in just a moment. So same process as before, whether you're using the calculator or the website. And just a reminder, if this example 3 was a real final exam question, I wouldn't have a part C. You would jump immediately to part D, and I would just write in, use the fact that critical number T star is this number, whatever it happens to be. We're only doing this in a homework setting or a quiz setting. So hit second bars, pull up your distributions, go to option number 4, and looks like we have to update one thing. That's kind of nice. If you're using this calculator for multiple problems, that's just one small change there. Let's delete all this stuff though. Degrees of freedom is 24. Oh, that would have been a faster way to go. Thanks for that. And this is what your calculator should look like before we go and hit enter. So hit enter a bunch of times like this. Takes a moment, and we've got a critical number. 2.0639 if we round to 4 places. This always looks weird, but it doesn't matter if you grab the positive or negative one, because the confidence interval uses both values. We just typically cite the positive value. So 2.0639. If we were using Z star, this would have been at 1.9600. So that's just a kind of a check for us at this point. The check is that should be larger than the Z star value at the same confidence. Any questions at all, folks, coming up with that figure here? Okay, once we have that, construction of the confidence interval, it goes about like this. Let's first write down y bar, add or subtract critical number T star, and then multiply it by standard error of y bar. So that's our full process, which means we're copying exactly what we did in chapter 13. I think I just need to grab this as a screenshot real quick. Just take a look at what your prior values were at the start of the problem. So for example, in place of y bar, we're putting in 513.32. Then we're adding and subtracting. For T star, go to the prior step, 2.0639. That 2.0639 multiplies the standard error. I'll use parentheses to indicate the multiplication. Throw in 52.446. So we did it, folks. That's our confidence interval. This right here is one of the major objectives in a course on statistics, just coming up with these intervals. So I'd say congratulations is in order. This is abstract work, but if you're up to this part, we're definitely getting through it. Let's now just toss it all into the calculator. And another reminder, in the calculator, just like in chapter 13, we're estimating mu now. Mu is constrained between two different values. We use the lower value first, the negative sign, to put the value into the left. So start with 513.32. We're going with a minus first 52.0639. A parenthesis for multiplication, 52.446. So here's my lower bound on the confidence interval. This is in money, so we could say about $405.08 upon rounding. Seems like they're stealing things like cell phones and iPads, for example, for the pickpocket amount to be up that high. Could be like a tourist destination where people are just not watching those things as carefully. So 405.08. Next, we repeat different ways to get this in your calculator. In a TI-83, hit second and the enter button. It brings on their line right above. Move over to the left and change to a plus. That's the upper bound in very, very minimal steps now. Upper bound is $621.56. And we did it, folks. That's our confidence interval. The confidence interval does a couple things. It gives us the best estimate of mu. The best estimate is in the center of the interval. It's 513.332. We added and subtracted this value. This is the margin of error to produce the whole interval. And now all we have to do is interpret it. It interprets essentially exactly the same way we interpreted them in chapter 13. We go up to what the parameter was. Let's take a screenshot just for emphasis. Kind of nice when the parameter doesn't have too much writing, I have to admit. And we start by saying this. With 95% confidence, now we're looking in the middle of the statement and we're just writing out what mu is. The true average amount lost to pickpocketing in this area is between those two figures, 405.08 and 621.56. So that finally ends the problem, and we've done it, folks. That's honest statistical inference at this point. This is the kind of stuff the FBI website does all the time with their data sets, looking into different areas and such. And so, well, not too much more left to say on this problem. Any questions or comments at the moment? Okay, these kind of problems go in two different ways. Sometimes we're given the summary information. That makes a problem a little bit fast, nice and streamlined. But other times, they look like this. They give us the raw data, and it's up to us to calculate the value of the statistics. We'll do this one next when we come back after exam 3. So we'll do this one in a week's time. That's kind of crazy to say, November 13th. Well, have a great night, folks. When we come back on Thursday's class tomorrow, we'll be reviewing for the third exam. Thanks, Madison.